Hello, students. So, what I'd like to start studying today is the analog of the Cauchy criterion for convergence of sequences of numbers to a criterion for convergence for sequences of functions. That is, I want to come up with some criterion that only has to do with terms of the sequence of functions that will be true if and only if the sequence of functions has a limit. That's what my goal is going to be. And, well, one of them, I think, will be pretty straightforward. So I'll try to do one for pointwise convergence and one for uniform convergence. The pointwise one will be pointwise Cauchy, and the uniform version will be uniform Cauchy. So let's start by trying to figure out what pointwise Cauchy should mean. So I'll be hopeful and say what sort of result I would like to be true. I would like a sequence f sub n to be pointwise Cauchy if and only if that same sequence, f sub n, is pointwise convergent. But notice, I know what it means for a sequence to be uniformly convergent. F sub n, no, pointwise convergent. I know what it means for a sequence of functions to be pointwise convergent. What does it mean to be pointwise convergent? It just means for all x in the domain, which I'll call u, f sub n of x, which is now a sequence of numbers, converges. But now I have a sequence of numbers. I have a Cauchy criterion for sequences of numbers. So this is true if and only if for all x in U, f sub n of x is Cauchy as a sequence of real numbers. So here is the definition of what it should mean for a sequence to be pointwise Cauchy. A sequence of functions f sub n from U to R is called pointwise Cauchy if for all x in U, the sequence of real numbers, f sub n of x. So here x is treated like something that's fixed, and I'm letting n vary. That sequence of real numbers is Cauchy. Expanding the definition of what it means to be Cauchy. So if you like, this is going to expand. I'll do it in blue. This bit. Let's expand that out. So that should mean for all x in U, for all epsilon bigger than 0, there exists a choice of big N such that for all little m and little n bigger than big N, the absolute value of f sub n of x minus f sub m of x is less than epsilon. So there's the definition of pointwise Cauchiness. A sequence of functions is called pointwise Cauchy if and only if, for every x in the domain of that sequence of functions, for every epsilon bigger than 0, there exists some big N such that for little m and little n bigger than big N, the difference between f sub n of x and f sub m of x in absolute value is less than epsilon. And just like before, what can this n depend upon? Well, it can depend upon anything that comes before it. So it can depend on x and epsilon. And if I say there's a definition of something, I want you to uniformize it, you know what I'm going to do. I'm going to rewrite that definition so that big N doesn't depend on the choice of x. A sequence is called uniformly Cauchy if that n depends only on epsilon. Said more formally, a sequence of functions is called uniformly Cauchy if, for all epsilon bigger than 0, there exists some big N such that for all x in U, for all m and n bigger than big N, absolute value of f sub n of x minus f sub m of x is less than epsilon. The first result, which we'll prove, will be a nice little warm-up result. I'll prove something that hopefully seems pretty obvious. I'll prove that if a sequence of functions is uniformly Cauchy, then that sequence of functions is pointwise Cauchy. And the idea of why that should happen, so what does it mean to be uniformly Cauchy? Well, it means that there exists a single choice of big N that walks, whatever walks means, for every x simultaneously. So how about this? So consider any x, consider any epsilon bigger than 0. Now use the big N that walks for every x, and any little m and little n bigger than big N, then you get the desired result. So the proof should flow through. Let's actually talk through it. Proposition 4.3.3. Let f sub n from u to r be a sequence of functions. If the sequence of functions f sub n is uniformly Cauchy, then it is pointwise Cauchy. And this is just going to be an exercise in definitions. So let's let f sub n from u to r be a uniformly Cauchy sequence of functions. I need to show that f sub n is pointwise Cauchy. How do you show a sequence is pointwise Cauchy? So you need to consider any epsilon bigger than 0, and then you need to do something for any x. But before I declare the x, let's actually just use uniform Cauchiness. There exists a single, there exists some n0 such that for all m and n bigger than n0, and all x in R, maybe I'll say u just to make it clear that it's the same u, that it's the same u, it's the same n0 for every u. For all u in u, absolute value of f sub n of u minus f sub m of u is less than epsilon. Now, so there's our line in which we've considered any epsilon bigger than 0, and there's just the definition of uniform Cauchiness. Now we'll consider any x in R, because that's what we need to do next. Let's let big N actually be the same as that n0. Then for all little m and little n bigger than big N, which is the same as n0, I get this statement holding for everything in the domain U. Oh, that shouldn't be U in bigger. That should just be U in the set U, right? Now we'll consider any x in the domain U. So as long as little n and little m are bigger than that big N0, then I get this conclusion for every U. There's a particular thing in the set big U, so let's use that particular thing. Cool, so that means that this thing is pointwise Cauchy. There are two things that I'm going to prove in this lecture as the main results. They're both going to be results that say convergent if and only if Cauchy. So I'll prove that a sequence of functions is pointwise convergent if and only if it is pointwise Cauchy. I will prove that a sequence of functions is uniformly convergent if and only if it is uniformly Cauchy. And that's it. So let's get started. And I'll close with maybe a little bit of homework comments. So let's prove the easy one first. Suppose that f sub n is a sequence of functions. Then f sub n is pointwise convergent if and only if that sequence of functions is pointwise Cauchy. And this proof is based on the fact that we know that for a sequence of numbers a sub n is Cauchy if and only if a sub n converges. So here, let's do it. Suppose f sub n is pointwise Cauchy. By the definition of pointwise Cauchy, that means that for all x in U, the sequence of numbers f sub n of x is Cauchy. All right, what does it mean to be pointwise Cauchy? Well, we have the definition right here. A sequence of functions is called pointwise Cauchy if and only for every input, the sequence of outputs f sub n of x is Cauchy. But what's the point of Cauchiness? The point of Cauchy sequences of numbers is that Cauchy sequences of numbers converge. So for any x, let's let f of x be the limit of the sequence f sub n of x. Now we have, for every x in U, f sub n of x is converging to f of x. That's exactly what it means for a sequence of functions to converge pointwise. There's half of the proof done. Conversely, let's suppose that f sub n converges pointwise. Let f be its pointwise limit. Consider any x in U. By the definition of pointwise convergence, I know that the sequence f sub n of x converges to f of x. Oh, but hey, Cauchy sequences of real numbers, convergent sequences of real numbers are Cauchy. So since convergent sequences are Cauchy, I can deduce that the sequence f sub n of x is Cauchy. But remember the definition of pointwise Cauchy, not the fully quantified version. This version. A sequence of functions is called pointwise Cauchy if for every x, the sequence of real numbers f sub n of x is Cauchy. Thus, for all x in U, f sub n of x is Cauchy. And so the sequence f sub n is pointwise Cauchy. Great. So I know this is a bit short. The next video will run a little bit long because I'm going to prove something a touch more involved. I'm going to prove that if f sub n is a sequence of functions, then f sub n is uniformly convergent if and only if it is uniformly Cauchy. Wonderful. Well, we will stop there. I'll talk to you real soon.